Hello, everybody out there in YouTube land. Good times for all. There's Zachary's about here if you prefer. In these Crocheter Corners, the last couple, I have been going over Walter Lewin's lectures of his 802 MIT physics classes. They cover electricity and magnetism. If you haven't seen, you're missing a little bit if you missed the second one. Not too much. We learned a little bit. The first one we learned a whole lot. 2 days. You're missing a little bit if you. Oh, sorry. Yeah, 2 days. Or we've done 2 lectures so far. And lecture number 2 really doesn't cover too much in the ways of how the Earth acts with the electric field. It was more how positive and negative or applying charges to an electric field and how they act. So it covered a little bit of stuff, but it'll be recovered again as we go forward. But number 1, if you haven't seen number 1, you really should. I'm going to play the beginning of his number 1 lecture, like the first 5 minutes or so, or 3 or 4 minutes. It's just him explaining what his class is going to be about and what electricity really is. It's a beautiful little segment, and just listen to his voice. Listen to the passion that this man has about teaching. Great teacher who was thrown under the bus by his peers. We all know when you're in the club, you can pretty much get away with whatever you want. You have enough money and enough power and know the right people. Well, he was one of these people. And then he was stripped of everything, his credentials, this guy had done all kinds of stuff. And it was all taken away. And he lost his tenure at MIT, all kinds of stuff. He was thrown under the bus, blackballed. And they don't do that unless you do something wrong. He has talked about the shape of the earth and how he will not discuss it. He says that he forgives you if you do not want to be his friend anymore, but he will not discuss it under any terms, which makes you think. I'm just going to leave it at that, but this is the beginning of his lectures, his class. Like if you saw him for the first time walking into his classroom, this is what you would hear him say when he went to go talk about electricity and magnetism. Let me share this.
Following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses,
here we go.
visit MIT OpenCourseWare at ocw.mit.edu.
Well, 802 is, of course, largely about electricity and magnetism.
Oh, wait, this
and
isn't
at the
the
heart of electricity and magnetism are the famous 4 equations. We call them the Maxwell's equations. And it's quite a difficult course for students. And I go out of my way to...
It's not bad, his little introduction, but that was kind of him talking, not him talking to his students.
Your heart would not beat without electricity. And you could not...
I was already in a ways.
The equations.
Okay, here we go.
I'm Walter Lewin. My lectures will in general not be a repeat of your book, but they will be complementary to the book. The book will support my lectures, and the lectures will support the book. You will not see any tedious derivations in my lectures. For that we have the book. But I will stress the concepts, and I will make you see beyond the equations, beyond the concepts. I will show you, whether you like it or not, that physics is beautiful. And you may even start to like it. I suggest You do not slip up, not even one day. 802 is not easy. We have new concepts every week, and before you know, you may be too far behind. Electricity and magnetism is all around us. We have electric lights, electric clocks, we have microphones, calculators, televisions, VCRs, radio, computers. Light itself is an electromagnetic phenomenon, as radio waves are. The colors of the rainbow in the blue sky are there because of electricity, and I will teach you about that in this course. Cars, planes, trains can only run because of electricity. Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could not see without electricity. Your heart would not beat without electricity. And you could not even think without electricity, though I realize that even with electricity, some of you may have a problem with that. The modern picture of an atom.
Okay. So that was him explaining what electricity is and does, and it's really it controls everything. Electricity literally controls everything that we see, hear. It controls chemical reactions. It controls everything. Without it, we would be lost. So we're going to jump into, now this is going to be a great lecture of his, kind of explaining Gauss's law, which is how it'll be electric flux, Gauss's law, and then examples. But this is an amazing lecture because he goes into how electricity would act on a sphere, on an infinite plane, on a plane with an edge. I mean, this is like flat Earth 101 electricity right here. This is the one that really, really, really got me hooked onto the Walter Lewin. I watched the first one and I was like, oh, wow, this is awesome. Then I watched the second one, the one we did yesterday. I'm like, oh, this is all right, you know? And then this one right here really grabbed my attention and made me go back and watch the first two again. And then once I got to this one, I mean, I watched the first 5 of these, and then I watched them over and over and over and over and over again. So here we go. This is 802, Lecture 3. Walter Lewin, amazing teacher here. But yeah, you'll see. This is stuff is going to blow your mind right here.
Today, we're going to work on a whole new concept, and that is the concept of electric flux. We've come a long way. We started out with Coulomb's law, we got electric field lines, and now we have electric flux. element which has this as a magnitude dA. Now our book will all.
Now again, there's going to be some mathematics at the beginning, of course. Little nuggets here and there. Yeah, I paused it for a sec. Let me see.
Always write for NDA simply.
Is it still there?
DA.
Is it back or?
So I will do that also, although I don't like it.
Sound still gone?
But I will follow the notation of the book. So this vector dA is always perpendicular to that little element dA, and it has the magnitude dA. And so this, since it is a dot product, is the magnitude of E times the area dA times the cosine of the angle between these two vectors.
Sound still?
Theta. It is a scalar. The number can be larger than 0, smaller than 0, and it can be 0. And I can calculate the flux through the entire surface by doing an integral over that whole surface. Of flux follows immediately from the definition. That is Newtons per Coulomb. So the units of this flux is Newtons per Coulomb times square meters. But no one ever thinks of it that way, just SI units. I can give you a
Yeah, I don't know what happened there.
Intuition for this flux by comparing it first with an airflow. These red arrows that you see there represent the velocity of air. And you see there a black rectangle 3 times. In the first case, notice that the normal to the surface of that area is parallel to the velocity vector of the air. And so if you want to know now what the amount of air is in terms of cubic meters per second going through this rectangle, it would be V times A. It's very simple. However, if you rotate this rectangle 90 degrees so that the normal to that rectangle is perpendicular to the velocity vector, nothing goes through that rectangle. And so it's 0. So now the flux, air flux, is 0. And if the angle is 60 degrees, then it is, of course, V times A times the cosine of 60 degrees. Now think of these red vectors as electric fields. But now the electric flux going in the first case through that surface is now simply E times A. In the second case, it's 0. And in the last case, it is EA times the cosine of 60 degrees. And so you can sometimes think of this as airflows. We also saw that when we dealt with field lines. That can come in sometimes very handy. I now take a surface which is not open as this one is. This is an open surface. Come in from both sides. But now I choose one that is completely closed, like a potato bag or a balloon.
Okay, now whenever he starts drawing like this is where it starts getting interesting, and it's not so math-based, and this is where you really learn all the little gold nuggets. So kind of pay attention to what he's saying right here.
I'll put this line in here to give you a feeling that this is a completely closed surface. So you can only get inside if you would penetrate that surface from the outside. And so now I can put up here and here these normals, dA. There's another normal here, maybe in this direction, dA. In this case, by convention, the normal to the surface, locally to the surface, is always from the inside of the surface to the outside world. It's uniquely determined because it's a closed surface. Here, it was not uniquely determined. I arbitrarily chose this one, but I could have flipped it over 180 degrees. Since it's an open surface, it's ill-defined. Here, it's never ill-defined. So the normal is always chosen, go from the inside to the outside. And now I can calculate the total flux going through this closed surface, locally multiplying E with dA, dot product, over the whole surface.
Yeah, maybe not this one. This one is still math-based. He's just explaining closed surface and open surface and how you would apply it to a calculation. Not all that.
Out comes a certain number.
Oh, and this is Walter Lewin, former MIT physics professor, flat Earth.
Now, therefore, the integral of E dot dA integrated over that closed surface, and since it is a closed surface, we put a circle here to remind us that it is closed integral. And here, in this case, it is a closed surface. And this now is the total flux through that surface. It could be larger than 0. It could be smaller than 0. It's a scalar, it's not a vector. It could be equal to 0. If it's equal to 0, then you can think of it, whatever flows in, if you think of it as air, also flows out. If more flows out than flows in, then it is positive. If more flows in than flows out, it is negative. So let's now calculate the flux for a very simple case.
Again, it's like the hairdryer. A positive charge is like, excuse me, is like a hairdryer blowing out, while a negative charge is like a vacuum sucking in.
Where I have a point charge. So here, I have a point charge, and I'm going to put a bag around this point charge, and the bag is a sphere. It is a sphere, and the sphere has radius capital R. And let this charge be plus Q, just for simplicity. Well, I pick a small element dA here, and that element dA radially outward. dA. This is the normal to that surface, so that is radial. The electric field at that point is also radial. We have dealt with that before. So the A and E, not only here, but anywhere on the surface of this sphere, are parallel. So the cosine of the angle equals 1. I can also introduce here the unit vector R roof, which is the unit vector going from capital Q to that element where I evaluate the teeny-weeny little amount of flux. So if now I want to know what the total flux is through this sphere, that's very easy. Because since this is a sphere, the E vector in magnitude is everywhere the same, because the radius is the same distance to this charge. And dA and E are parallel. So it's simply the surface 4 pi r squared of that sphere times E. And so now I have that the total flux through that closed surface is simply 4 pi r squared times E. Well, what is E? The electric field.
Come on.
At this distance r.
Like I said, you got to shift through a lot of nonsense to get to the gold nuggets.
Q.
But this is their,
by 4 pi,
their mathematical.
R squared times R roof. That gives me.
Yeah, this is the stuff where you just. I try to pay attention as best as I can, though, because there are little nuggets that he'll drop every once in a while when he's explaining this stuff.
And I find that the E vector, at least the magnitude of the electric field, that the flux phi, that's what I want to calculate. I multiply this by E equals Q divided by epsilon 0. And this is independent of the distance r. And that's not so surprising, because if you think of it as air flowing out, then all the air has to come out somehow, whether I make the sphere this big or whether I make the sphere this big. So the flux being independent of the size of my sphere, the flux is given by the charge, which is right here at the center, divided by epsilon 0. Now, if I had chosen some other shape,
Okay, this is
not
where
a
it gets
sphere,
good.
but I've dented it like this, it's clear
Maybe not.
that the air that flows out would be exactly the same. And so I don't have to take a sphere to find this result. I could have taken any type of strange closed surface around this point charge, and I would have found exactly the same result. And if I put more than one charge inside this potato bag, then clearly, since I know that electric fields from different charges can be added, should be added vectorially, it is clear that the relation should also hold for any collection of charges inside the bag. And therefore, we now arrive at our first milestone in 802, which we call Gauss's law.
Gauss's
Gauss's
law.
law says that the flux, the electric flux, going through a closed surface, being the closed surface of E dot dA, is the sum of all charges Q which are inside the bag that you may choose at any time you pick that bag, divided by epsilon 0. And this is the first of 4 equations of Maxwell, which are at the heart of this course. So the electric flux through any closed surface is always the charge inside that closed surface divided by epsilon 0. And if that flux happens to be 0, it means there is no net charge inside the bag. There could be positive, there could be negative charges, but the net is 0. Gauss's law always holds, no matter how weird the charge distribution inside the bag, no matter how weird the shape of this bag, it always holds. But Gauss's law won't help you very much if you don't have a situation whereby the charges are distributed in a very symmetric way. Gauss's law holds, but it doesn't do you any good if you want to calculate the electric field. In order to calculate successfully the electric field, you do need forms of symmetry, and there are 3 forms of symmetry that we will deal with in 802. One is, of course, spherical symmetry. Another one is cylindrical symmetry. And a third one is flat planes with uniformly charged distributions. Then we also have situations of symmetry.
Okay, that's where it's, this is where, all right, Flat Earth, take it easy, man. This is where it gets real interesting right here. This is where it's, where the shape of the Earth starts coming into play and where things start, he kind of explains here that the way electricity works and we understand it, we cannot have an infinite plane. That there almost has to be an edge if the charge does what they say it does. But we'll see. There's going to have to be a lot of tests and stuff done like that. But yeah, this is where it really gets shape of the Earth related and how electricity works. So start 1340 in, and it starts getting good finally.
And so now I would like to, as a first example, use an application of Gauss's law, and I will start with a situation of spherical symmetry. And I use a thin shell, a hollow sphere, which is thin. So this radius is r. And I put charge Q on here, but it is uniformly distributed. That's crucial. If it's not uniformly distributed, I have no symmetry, I can't do the problem. So it's uniformly distributed. We will learn later in the course that it's very easy to do this because any conductor of this shape, if you bring charge on it, will automatically distribute itself uniformly. So we have the charge plus Q on there, uniform.
So on a perfect circular sphere, the charge will gather on the outside edge uniformly. It will be the same charge all around the outside of that sphere, any place on that sphere that you touch it. Any charge that is applied to a conducting sphere like that will uniformly distribute that charge all the way around the outside edge shell.
You distribute it, that's a must. And I would like to know now, what is the electric field here at a distance r from the center? And what is the electric field here at a distance r from the center? In other words, I want to know what is the electric field everywhere in space, just due to this charged, uniformly charged sphere. And with Gauss' law, just goes like that. You now have to choose your Gauss surface. And if you don't choose it in a clever way, you get nowhere. In a case like this, I would think it is rather obvious that the Gauss surface that you would choose are themselves spheres, concentric spheres. If you want to know what the electric field is at this point, you choose a sphere with this radius r going through that point. If you want to know what it here is, you choose a sphere going through that point. All the way enclosed. It's a concentric sphere. And now you have to use symmetry arguments. And the symmetry arguments are the following. Since this is spherically symmetric, this problem, if you're here, whatever the electric field is here in magnitude must be the same as it is there, and it must be the same as it is there, because of the symmetry of the problem. Couldn't be any larger here than it could be here. That's obvious. That's the symmetry argument, because the charge here is uniformly distributed. That's symmetry argument number one. Now comes another symmetry argument, and that is the electric field, if there is an electric field, must be either radially pointing outwards or radially pointing inwards. So either it has to be like this, or it has to be like this, and here the same, either like this or like this, because we already know if this is a positive charge, that it's going to be pointing outward. It cannot go like this or like this, because nature could not decide in this spherically symmetric problem to go like this or like this. It can only go radially. That's the second symmetry argument.
So electricity always comes off of an object radially. It will not come off at an angle, at a, you know, it's going to come straight off from the center of the sphere and go straight out. Symmetrical.
So now, if we go to this sphere now, and we know that E is radially outwards, apart from a plus or a minus sign, apart from the fact that the angle between dA and E could either be 0 degrees or 180 degrees, we know now that the surface area of that sphere, which is 4 pi r squared, times the magnitude of the E vector right here. I can do that now because dA and E are either parallel or anti-parallel. That must be equal to Q inside divided by epsilon 0. There is no Q inside, so E must be 0. That's an amazing result. You say, well, there's no charge inside. Still an amazing result, because it means that anywhere inside here, no matter what radius you choose, the electric field equals exactly 0. And it means there is some crazy conspiracy of all these charges that are uniformly distributed here, which each individually contribute to the electric field inside through Coulomb's law, that all those together, through a conspiracy, make the E field everywhere inside 0. It's a non-trivial result.
And he will show this to us. So the inside of a hollow sphere, like the ionosphere, cannot produce a charge, whether it be positive or negative. The inside of a hollow sphere will always be 0. This is a law. So how does the ionosphere work? How are we getting a positive charge from above when all of those charges should be being expelled out into space?
All right, so now we know that the E field inside is 0. So this is for R smaller than R. Let's now go R larger than R. Everything I told you holds for the sphere, which is outside this hollow sphere. Everything holds. The E field here must be the same everywhere on the surface. The A and E are either parallel or anti-parallel. So I can write down again that 4 pi r squared, which is the surface area, times the electric field vector, must divided by epsilon 0. But this Q is that Q. It's not 0. There is charge inside. And so now I know that the electric field E, in terms of its magnitude, is Q divided by 4 pi r squared epsilon 0. And we know the direction. If it is positive, of course, it is radially outwards. And if this is negative, it's radially inwards. And this is a non-trivial result. We have seen this before. If I had put all the charge right here at the middle, at the center, we would have gotten exactly the same answer. We've seen that before. In other words, whether the charge is uniformly distributed over a sphere, or whether the charge is all of it exactly at the center of the sphere, that makes no difference for the E field as long as you're outside the sphere.
Okay, did you hear that? It doesn't matter where the charge begins. As long as you're on the outside of the sphere, it will always be equal. And on the inside of that sphere, it will always be 0. This is Gauss's law.
If you plot the electric field as a function of R, and if here is capital R, and if this is the field strength, then you would get that the electric field is 0 inside, jumps to a maximum value, and this falls off as 1 over R squared, proportional to 1 over R squared.
I'm not even sure what, I know what the 1 over R squared and all that kind of
If
stuff.
I go back to the situation that the charge, that the electric field inside is 0, you may say, isn't that a little bit of a cheat? Because, yeah, there is no charge inside, but have you really used the charge outside? And if you have used it, how did you use it? Well, I have used it. I use it through my symmetry arguments. The symmetry arguments take into account that the charge is uniformly distributed. If the charge on the sphere had not been uniformly distributed, I could not have used the symmetry argument, and therefore the electric field inside would in fact not have been 0. If there is more charge on the sphere here than there is there, the field inside the sphere is not 0. So I have used.
So it has to be symmetrical. It has to be symmetrical for the charges inside to remain 0.
Used all that charge by using my symmetry argument. Gauss's law and Coulomb's law, in a way, are the same law. They both link the electric field with the charge Q. Key is the fact that the electric force falls off as 1 over R squared. If the electric field strength did not fall off as 1 over R squared, Gauss's law would not even hold. And the electric field inside this uniformly charged sphere would not be 0. So it is the immediate consequence of the fact that electric forces fall off as 1 over R squared. Gravitational forces also fall off as 1 over R squared. Therefore, if you take a...
Now, is that amazing? The electric forces and the gravitational forces are parallel by how they get weakened. And they're parallel on how they act. He says this a couple times about how the electric field is and the gravitational field are parallel in so many different ways.
A planet, if it existed, which is a hollow spherical planet but hollow inside, it means there would be no gravitational field inside that hollow planet. So if you were there, there would be no gravitational force on you, if it is spherical. If that planet were a cubical planet, then the gravitational field inside would not be 0. You say, well, big deal. With 801, we always take a planet, and then as far as we're outside the planet, we put all the mass and we consider it as a point. Yeah, indeed. Not a big deal for you.
Now notice, when he's talking about gravity, he's always talking about planets, you know, and being well outside the planet and measuring the gravity out there.
And it is not a big deal for me, but it was a big deal for Newton. He intuitively sensed that it was correct, that if you have a planet, uniform mass distribution, that you can consider it as a point mass, as long as you're outside the planet. But it took him 20 years to prove it. And he finally published his results. It would take us now 30 seconds. He didn't have access to Gauss' law. Came about 100 years later. But the net result is that you see here in front of you that if you have uniformly charged distribution, and you can draw the parallel with gravity, that you get the same electric field outside that you would have gotten if all the charge is at one location, at the center. This is spherical symmetry number one. That's the easiest symmetry that we have in 802. Now I will present you with a second form of symmetry, which is a flat horizontal plane. And I want you to work out most of it, but I'll help you a little bit to set it up.
Now this is where you need to think about how the Earth works, the electricity on the Earth works, and how we can apply it to our ideas on what this place really is. This is my favorite part of probably all the lectures right here, is what he's explaining.
Suppose we have a plane which is very, very large. Think of it for now as infinitely large. It doesn't exist, of course, infinitely large. And I put on this plane charge. And I put a certain amount of charge density, which I call sigma. Sigma is an amount of charge Q per area A. So it is a certain number of coulombs per square meter. And it's uniformly distributed. So the whole plane everywhere has the same number of coulombs per square meter, or micro coulombs, or nano coulombs, whatever you prefer. And this is a plane which is huge, and you are being asked, what is the electric field anywhere in space? Just like we asked, what is the electric field anywhere inside the sphere and anywhere outside the sphere? Now I want to know what it is anywhere in the vicinity of this plane. If now you pick clever Gauss surface, the answer pops out very quickly. If you would choose a sphere as a Gauss surface, you're dead in the waters, you get nowhere, because there's no spherical symmetry. I will define for you that Gauss surface, but I want you to work out at home how you get the electric field. Suppose I want to know what the electric field is at a distance d above the plane. What I do now is I choose this as my Gauss surface. Watch me closely. This is the intersection with the plane. This is my Gauss surface.
Now think about this. He starts talking about things underneath the plane. Listen to what he says about this right here. Now what he's doing, he's trying to measure this surface right here, this area, that whole area. And he has connected it with the plane and has also gone about an equal amount the opposite side of the plane. Very, very important. Listen to what he says right here.
It is a closed surface. 3 conditions have to be met for you to be able to calculate what the E vector is at that location D. The first one is that this is a flat plane here, and this is the same flat plane, must be parallel to this plane. That's a must. You don't do that, you can't use Gauss' law. The second one is that these vertical walls that you have here are indeed perpendicular to that plane. In other words, these are parallel, and these are exactly vertical. If you don't make them vertical, if you do this, dead in the water. Can't use Gauss' law very effectively. And then the third argument, which is very important, that this flat surface is a distance d above the plane, and that this flat surface is exactly the same distance below the plane. You can already smell why that is important. Because if you ever want to use a symmetry argument, if this plane is uniformly charged, the electric field vector here, in terms of magnitude, obviously must be the same as there in terms of magnitude.
Okay. So any charge above the plane has an equal and opposite charge below the plane. When I heard that, I was like, wow, that kind of reminds me of as above, so below. So we are a charge above the plane. You are putting off a charge above the Earth. So is there an equal and opposite charge on the other side of the dielectric plane? Hey, Stephen, welcome. Is there a... This is what really blew my mind right here. And he goes on and talking about if the plane were infinite, if the plane isn't infinite. Yeah, this is good right here. Check this out.
Maybe not in terms of direction, as long as this d is the same as that d. That's why it's important that the two d's are the same. The charge that you have inside when you apply Gauss's law is the charge which is, of course, here. That's the only charge inside that closed box. If you work this out at home, you will find an amazing result. You will find that the electric flux through these vertical walls, zero. Nothing comes out through the vertical walls. Think about it, why that is. Use symmetry arguments. But something comes out here or comes in here if it is a negative charge, and something goes out here. And so you only have two contributions from those two end plates. You'll work on that, and you will find, perhaps to your amazing result, that the electric field equals sigma divided by 2 epsilon 0, that it is independent of how far you are from that plane. Whether you're very far away or whether you're close, it's the same. So if this is that plane, and if the plane is positively charged, then E would be like this here, and E would be like this here, and it would be independent of distance. And if it is negatively charged, E would be like so, and it would be like so, pointing towards the plane, and in all cases, would the magnitude be?
So our plane is negative, right? We have a negative plane, and we are sucked to the plane, right? We are not being pushed off the plane in any way. We're actually being pushed into the plane of our negatively charged ground.
Sigma divided by 2 epsilon 0. Does it mean if I go very far away from that plane that it is still independent of the distance? Yeah, if that plane is infinitely large.
Okay, did you hear what he said there? If the plane is infinitely large, it does not matter how far away you go, the charge will always be there. If it is infinitely large. If it is not, eventually it will become a point source and it will fall off at 1 over r squared like a sphere does.
But if the plane is only as large as the lecture hall here, then clearly it would hold very accurately as long as I stay relatively close to the plane. In other words, if my distance to the plane is small compared to the linear size of the plane. But if I go miles away, well, of course, then that plane is charged, looks like a point charge. If I'm 5 miles away from 26,100, if the plane is only as large as this lecture hall, then it looks like a point charge. And obviously, the electric field will then fall off as 1 over r squared. So when I say the E field doesn't change with distance, it means, of course, that you have to be relatively close to the surface, relative to the linear size of that surface. So you are going to prove this, and I'm going to use this now to calculate for you a much more complicated configuration of two charged planes. But I use that result.
Now this is where it gets really, really, really interesting. Just think about it. We have a positive above our heads. Not exactly sure where it comes from, but we have a positive and a negative below our feet. Okay?
That's very important. And suppose I have here a plate, very large. Nothing is infinitely large, of course. And it has a...
Did you hear what he said there? Was that a slip to tell you? Nothing is infinitely large. Nothing is infinitely large.
Surface charge density plus sigma. And I have here a plate which has surface charge density minus sigma. And the separation between these two plates happens to be d. And the question now is, what is the electric field anywhere in space? Here, here, and here. And we'll think of...
Now, what he's explaining is, okay, we have these two plates. Now, what is going to happen below this plate and what is going to happen above this plate? This is where I start thinking about space. Say these are just charged plasma fields, maybe. It doesn't have to be a solid object, just a charge. I'm not sure how it would happen. But just think about like our Earth. And if we were to get above this charged plasma plane, would there be an effect? Would we just start floating? Would the signs cancel each other out? And you'll see. Here, watch this.
Think of them as being infinitely large, each plate. And I now use the superposition principle. I say to myself, aha, this plate alone, forget this one, this plate alone would give me an E vector, oh, stick to my colors, give me an E vector like so, and that is sigma divided by 2 epsilon 0. This one is also pointing away from this, sigma divided by 2 epsilon 0, and here it's also sigma divided by 2 epsilon 0, because it's independent of the distance to this plate. What?
So the positive plate, even below the negative plate, is still putting off a charge and affecting the flow of electricity there.
What is the negative charge doing? Well, the negative charge has E vectors pointing towards it. So here I have an E vector, which is sigma divided by 2 epsilon 0. Here I have one that is sigma divided by 2 epsilon 0. And I have one that is pointing towards the plate, which is sigma divided by 2 epsilon 0. I use the superposition principle. I can add electric vectors. And when I do that, I find that these two cancel each other out. So the electric field here is 0. The electric field here is sigma divided by epsilon 0. The two support each other. They are both in the same direction. And the electric field here is again 0.
So look at that. You have the positive above flowing to the negative below, and everything above that positive plate cancels out, and everything below the positive plate cancels out to be 0. But within that plate, they work together. Within those two plates. Now, he said these were infinite, so everywhere within there would be equal. Kind of like the gravitational field, right, that they say exists. It's equal pretty much everywhere on Earth. You know, it's all across it. And the only way that it wouldn't on planes is if you got near the edge. And then things start getting a little bit crazy. But this right here, this is what I think we are living between. We have a positive plate and a negative plate beneath us. positive plate above. The electric field, the flow of the electric field, which is parallel to gravity, but 26 times stronger than gravity here on Earth. The only time gravity takes over is when we start going out into outer space. That this is what holds us to the Earth right here.
And that is an amazing result. Of course, it's only accurate if these plates are extraordinarily large. And so if I have to draw the field lines in a situation like this, then the field lines would be like so if the upper plate is positive. And the field in here would be the same everywhere. It would be outside 0 and outside 0 here.
Now he'll get to the edges. But anywhere within this plane right here, it is all equal. Like he'll show you, once you get near the edges, it'll start looping around and doing crazy stuff. But as long as, say the Earth were just within the Earth we know, we're within these 3 lines right here, our puddle. Gravity, or the electric field, would be equal everywhere. The only thing that could change it is elevation change. Stuff like that.
Now, clearly, this cannot be true if you get into this area here where you are near the end of these plates. That is not possible. Why not? Well, you can't use your symmetry argument. So Gauss' law is not going to help you if you get anywhere near this area. And it is very difficult to calculate the electric field configuration when you are near the edges, which we call the fringe field. Maxwell, of course, was a clever man, and he knew how to do that. Today, we can also do that very easily with computers. But I'll show you from Maxwell's
mathematics
publications that in a situation like that, he was already perfectly calculating these electric field lines. And you have these 2 horizontal plates, which one is plus and which one is minus, doesn't matter. He doesn't put arrows in there. And what you see is an extremely strong field inside the 2 plates. Remember that the density of field lines tells you something about very strong field, but when you get near the edge, the field is not really 0. The field strength drops very rapidly because look, the density is very low, but it is not 0, and the electric field is not 0 here either, and is not 0 there. In our assumption, in our simplification, we have, however, assumed that the plate is so large that we don't have to worry about any end effects. And in that case, the electric field is only existent in between the plates, but not anywhere else. I now want to demonstrate to you some of the things that we have learned today. And the first thing that I want to demonstrate is that the electric field outside a large plane is more or less constant.
Okay, this is where it starts. Now you got to remember that when distilled rainwater and stuff like that, like if you're thinking about this with our cosmology, so many things, particulates in the air, things like that. Pure rainwater is actually, it doesn't conduct. It's actually an insulator. So you got to take all these different things into account when you're trying to apply this to our cosmology here on the plane and how electricity works here. It's very, very complicated, but this is like the basics. And then you add stuff to it.
Doesn't matter how far away you are. Now, the way I'm going to do that is, of course, I don't have an infinite large plane. The plane that you're going to see only a few square meters in size. And so it's only something like 1 by 1 meter. Then it would only be true that the electric field is very close to constant if I stay very close to that plane. The moment that I go out as far as a meter, of course, it's no longer true. So
see, this is what makes me think that there could be an edge. Because the electric field, supposedly, actually It gets stronger though as we go up. I'm not really sure. I'm not sure. It makes you wonder how close we are, how far away the plates are.
It's very qualitative what I'm going to show you. But
this is why I want to start measuring the electric field myself, because the way they do it is mostly based on math, and I think this could tell us a lot about where we live.
You're going to see very shortly there a very large plane. We're going to get it in a few minutes. And let's assume that we look at that plane edge on. So here is that plane. Look at it from edge on. It will be put here. It will block your view. That's why we don't have it up now. And what I will do now is I will connect that with the Van de Graaff, which is behind it. If you wait a few minutes, then clients will pay attention to me and not to you. Here's the Van de Graaff. We're going to attach it to the Van de Graaff. And then we use this interesting fishing rod, which is a small mylar balloon, which we will charge with the same charge as the Van de Graaff, the same charge as the plate. And we will hold that in front of the plane. And then, of course, there will be a force. So here is my glass rod. This is the vertical. And because there will be a repelling force on this air-filled balloon, there will be an angle. There's an electric force on it because the two have the same charge. And this is the angle theta that I will show you projected on that wall. And when I move this away from this plane, you will see that the angle theta becomes smaller. Yes, of course, because look how small that plane is. No matter what I do, if I go from 20 to 40 centimeters, you can't really say that the plane is infinitely large compared to 40 centimeters. But you will see that the angle of theta will change very slowly. And then we will remove that plane, and then we will do exactly the same experiment, but we will use only the Van de Graaff, which produces now an electric field. And that electric field now falls off as 1 over r squared. It's not constant as a function of distance, but it falls off as 1 over r.
1 over r squared is so important. This is the, excuse me, inverse square law. This is light. This is how light acts, which is also electricity. It just shows you electricity has a certain way that it works. It's like a living thing. It's beautiful. And we still don't understand most of it. I still don't think we grasp what's really going on. We have ideas and stuff, and we can manipulate it somewhat, but yeah, there's so much more to learn about electricity, to discover, I should say.
Squared. This is a hollow sphere. So you can think of it as all the charge right at the center, as we demonstrated on the blackboard still here. You know, you get that amazing result. And so now, if I place this fishing rod, this balloon, near the spherical Van de Graaff, you will see that this angle theta drops very fast when I start moving my hand away. Extraordinarily fast. If I double the distance to the center, the force on that little object will become 4 times smaller. It's inverse
square. Yeah.
So let's first do the plane, and then we'll try to do the single Van de Graaff. And we'll try to optimize the light conditions. We have a projection here. There's a carbon arc, which will...
In my fun with electricity, I did a bunch of, made a bunch of observations using pizza trays and a single plane with a charge on it, dual planes with opposite charges on them, the sphere. I did all kinds of observations on how the electric field works with different materials. Pretty cool stuff. You check it out if you want.
Hopefully produce some light in that direction.
Playlist, Fun with Electricity in my playlist. So you don't have to go looking through a bunch of videos.
Direction. if the carbon arc works. Marco, oh, I forgot to turn on the power. Thank you. So this carbon arc is coming on now, and you'll see there the shadows on that wall. See my hand? Here is that plane, and it is far from infinitely large, that plane. If I were this far away from it, 4 centimeters, very close approximation, it would be infinitely large. But if I'm here and there, and that's where I will be, of course, it is not infinitely large anymore. So let's start the Van de Graaff. You can't see it, but I turn it on. It's rotating now. I have to put charge on here, so I'll touch it with the Van de Graaff. And so this is now charged. It has the same charge as the plane. The plane is being charged. And here you see the angle. Try to remember that angle. Hard to estimate, maybe 15 degrees. You see the vertical. And if now it's about 30 centimeters away from the plane. And if now I go back to 50 centimeters, which is where I'm now, you see the angle hasn't changed very much. If I go further out to 60 centimeters, yeah, the angle goes down a little. Of course it does, but not very much. And if I go far away, all the way to Mass Avenue, of course, the force on this little object would be inversely r squared, because then the whole plane would behave like a point source. So I've shown you that very close to this plane, the electric field stays approximately constant. So if now we remove this, Marcos, if you can, yeah, we'll have to take this also off. Thank you very much. So now we have the Van de Graaff alone. So now we know that the electric field falls off as 1 over r squared. That's a very good approximation now. We can think of the charge as being right at the center. I will give it a little bit of charge. Oh, it is already charged. Okay. So look at the projection. The balloon is now, maybe 30 centimeters away from the center, maybe 40. Oh, the angle is almost 45 degrees. And now I double the distance. I go to about 90 centimeters. And look at that angle theta. The angle theta is now down to, maybe 10 degrees. I will go back where I was. This angle is about 40 degrees. And now, very small. And when
This is what really grabbed my attention. I want to measure the electric field at high elevations and see if it falls off at the rate that it's supposed to. But again, there's so much stuff else that you have to calculate into it. It won't be easy. But I think there's some answers here in the electric field.
go here, which is about 1.5 meters, you can hardly see that there's any angle. It's only a few degrees. And so I've shown you only qualitatively that the electric field falls off very rapidly in the vicinity of a hollow, uniformly charged sphere, and that it doesn't fall off very fast if you are in the near vicinity of a plane. The second thing I want to show you has to do with the fact that the electric field inside a uniformly charged sphere is 0. Here I have a sphere which is not entirely closed. I can't make it closed because I want to demonstrate to you that there is no electric field inside when I charge it uniformly. And since I have to get inside, I need an opening. There's nothing I can do about it. Since there is an opening, the electric field is not exactly 0 inside. It's only true if this is a complete closed surface and if the charge is uniformly distributed. But it's a good approximation. The opening is quite small. And what I'm going to do is I'm going to charge this sphere. I'm putting charge outside. I use a device that we have not used before, but that's not so important. But here is now that hollow sphere. I'm going to put charge on there. Let's suppose it is positive charge. So this will be positively charged. Since it is a conductor, as we will learn I think the next lecture, or at least this week, that the charge will automatically distribute uniformly. Only does that on a conductor. And now, to demonstrate to you that there is an electric field here, I will use induction. I have two ping pong balls painted with conducting paint. They touch each other. Under influence of this electric field, this one will become negative and this one will become positive. We've discussed that last time. You create a dipole. It's not important that it is a dipole. I separate the two. I have negative charge here and positive charge there. I will touch any one of these two balls, it doesn't matter which one, with the electroscope, and you will see that there is charge there. So I have demonstrated then that there is an electric field outside that sphere. Now I will do exactly the same demonstration, but now I put these two inside. So here they are. I touch them. You just have to trust me that I really will touch them. And then I will take them out. And if I didn't make a mistake, if I didn't touch the rim by accident, then I will show you that there is no electric field inside. It means there is no induction. So these balls did not pick up charge. I show you with the electroscope that indeed there is no charge on it. So that is the way I want to do this. So there's the electroscope. Here's the sphere. And the way I'm going to charge it as a...
So he's showing you Gauss's law right here. He's showing you that inside of a hollow sphere, there is no charge on the inside of a sphere. All the charge, negative, positive, does not matter. All of that will gather on the outside of a hollow sphere. Kind of like our ionosphere, right?
It's a nice name. It's called electrophorus. Hard to pronounce. I first rub a glass plate with cat fur. Then I take a metal plate, I put on top, and I touch it with my finger. And now I transfer charge. And you think about it, why that is. I put it on here again, touch it again with my finger. I'm again charging it. Put it on top.
And he's not joking. This actually works. I've done it. I have an electrophorus. He'll explain to you in a later lecture how it's all working. He's really, I mean, it's got a charge on the plate because it's picking up a charge from the glass. But him touching it is then bringing all the positive to him because he's grounded and leaving the negative on the other side of the plate. It's amazing. I don't know how it actually works, but it does. It actually puts a positive charge on one side of the plate and a negative charge on the other side of the plate, depending on what surface you're using. He's using glass, which is a positive.
Touch it again with my finger. I want a little bit more charge. So I'm rubbing this again. Put this on top. Touch it with my finger. Every time I do that, I feel a little shock. Put it on there. Touch it with my finger. Okay, let's hope that's enough. So now comes demonstration number one. These two spheres conducting, completely discharged. I bring them close to this sphere. There they are.
Now he didn't touch it.
Separate them.
See that?
Now
so he created a dipole.
Shall I use this one or this one to touch the electroscope? The same to me. My right hand or my left hand? Who wants right? Who wants left? The right one's
now, positive or negative, you're going to get a charge.
There's
no matter
the charge.
What.
So I've shown you that there is an electric field there. Through induction, I've created charge on here. Now I'll do the same inside.
Now he should have showed you. If he would have touched it with the other one, the charge would have went back and lowered.
Because if I hit the rim, then it's not zero. This one has to go in first because the opening is too small.
Now listen, okay.
And the second one.
Now remember, this guy was blackballed. He was thrown under the bus by his own people. He was definitely in the club. And he was chastised and thrown out of MIT, and all his accreditations were taken from him. So he had to have done something, all right? And the way he teaches, he is a very honest man and a very good teacher. I don't think that he actually wants to be deceitful, but he has to in order to, you know, it's almost like there's a turmoil going on inside of his mind about wanting to be good, you know, and but listen to what he says right here. Listen to how he says it. He says, I would not lie to you, not about this. Which to me, he is admitting that either I have lied to you in the past or I am going to have to lie to you in the future. He's very honest about how he says it.
Has to come in. Now I have to touch them. And I really do. I wouldn't cheat on you. Not this time.
Not
They're
this
now in
time.
contact with each other. Now I take one out. And I take the other out.
I would not cheat on you. Not this time.
Which one shall I touch it? There shouldn't be any charge on either one of them. We had left before or we had right before? Well, let's do this one. This one? Who is for left? Who is for right? The left have it. Nothing.
Little tiny bit of charge
Little bit. Well,
because the hole.
Inside is not necessarily exactly zero.
Because there's a hole. It has an opening on it.
The last thing I want to show you has to do with the fringe field that we have seen here. I have here two parallel plates, which I'm going to charge with an instrument that we have not seen before.
I want one of these.
Which is called the Wimhurst.
Wimhurst
If I rotate
device.
this crank, I can produce positive and negative
A
charge.
Wimhurst generator.
And this plate becomes positively charged, and the other plate automatically becomes negatively charged. And I'm going to show this to you right there. That's the idea. Yeah, we'll make it. So there you see these two plates, and you see a ping pong ball. And this ping pong ball is a conductor. We put conducting paint on it. And remember when I did the demonstration with the balloon, which bounced between my head and the Van de Graaff, and every time that it bounced on the Van de Graaff, it took all the charge of the Van de Graaff, and when it bounced from my head, it took my charge, and so it went back and forth, and that is what I want to show you now, that this ping pong ball will start to probe that field first outside the capacitor, or I shouldn't use the word capacitor, but these plates, and then I will bring the ping pong ball inside, and then you will see that the field is much stronger there. So let's first get some charge on there. And listen to the sounds. Every time that it hits, it bangs. So it's following almost those field lines. And in doing that, it's actually transferring.
And this
charge
is so neat.
every
Yeah,
time
there
from
is
one plate to
there
the
is
other.
no motor here, folks. Moving that thing, the string isn't moving. It's just laying there. The only thing moving this ball back and forth is the electric field. It is the charge. It's gathering a charge from this plate that's positive and charging this to become positive almost instantly. So it's boom, it bounces away. And then it follows the electric field line over here and it's attracted to the negative and hits it. And then that instantly charges this as a negative and boom, shoots it out around, and it'll keep bouncing back and forth with just the electric field bouncing it. It's amazing.
It's nicely going around in an arc, the way you see it there. So it's clear that there is an electric field outside. I've proven that to you. Otherwise, it would never do what it's doing. So the electric field outside is not exactly zero. Of course not. This plate is not infinitely large. Now I will bring this ping pong ball inside. I have to open up the gap a little.
What a cool toy.
Now we'll bring it inside.
Look at that.
And you see the field is much stronger.
So you have positive, negative, or vice versa, and induction taking place really fast back and forth in between. And what's happening, same thing. It's hitting this plate, becoming charged, and pushing away from the plate, coming over here, becoming charged negatively and then pushing away from the negative charge, just back and forth. And the stronger the charge, the faster it'll do it.
Now it's going back and forth between those very high density field lines, very strong electric field, going back and forth. Each time that it hits the plate, it changes polarity. And this is not too different from the experiment I did with the balloon when I bounced it back from the Van de Graaff to my head and back to the Van de Graaff. Okay, stop working on that assignment. It's not an easy assignment this week. See you Wednesday.
Okay. Great lecture by Walter Lewin. It's these early lectures really relate to how electricity works here on Earth. Later on, you'll start getting into capacitors and resistors and transistors and all this other kind of stuff that is used in, you know, the scientific equipment or the technology that we use today. There will be a lot of that kind of stuff. But this early stuff is just, that's why I watched the first 4 or 5 of these things so many times. It's all about how electricity works naturally. And just not harnessing it, not, you know, us not manipulating it at all, just how it works around us. That's why I think it's so smart and or so important. And there's so many answers waiting to be discovered in electricity still that I think would be so pertinent to where we live and the shape of this place that we live upon. Like I said, like he said before, electricity controls everything. There's nothing electricity doesn't control. It is, you know, where everything comes from. It's where everything goes. It controls everything. And this one especially got into how the electric field would work on an infinite plane, on a limited size plane, and on a sphere. And I think just with that, we can show that we don't live on a sphere if we can actually start measuring this electric field properly. I think there's so much that can be discovered if we start applying this to our thoughts. But that's going to be it for today. Walter Lewin is an amazing, I know this stuff is boring, folks. I know. You really got to love electricity and stuff like that to sit through all this stuff. So those of you who have, thank you so much. I appreciate it. But yeah, I hope this helped, or I hope this is going to help make people think a little differently about some certain things. If you didn't see it, the first Crocheters Corner on this status, on this this topic, he explains how the electric field is what holds Earth together and everything together that we know of for thousands of kilometers, and gravity doesn't take place until talking about the sun, moon, stars, planets, solar systems. And that's so huge. I think people need to realize that stuff, that this is where we're going to get the answers, looking into electricity for so much stuff. So I guess that's it, folks. Thanks for joining me. I hope you go back and watch a couple of these, even without me. It helps, believe me. I've watched them all plenty of times. But yeah, Walter Lewin, again, great teacher, thrown under the bus by his own people for some reason. And has openly stated that he is refusing to speak about the shape of this place we live. Almost as if he cannot. So that's it, folks. Thanks for joining me, and this is Good Times for All signing out. As always, thanks for watching.